Hello. Today we're going to take a look at finding exponential growth and decay. So the first concept we're going to take a look at is pairing exponential growth or decay, I guess you could say, with money or with accounts and things like that. Now, we have two different formulas for this depending on what kind of account that we're using. The first one that we're interested in is this one, where we have A is equal to P times 1 plus R over N to the NT power. So our A is the amount that we would get after things were happening. P is our initial deposit. Our interest rate is R, the number of years that have taken place over time would be T, and then the number of times that is compounded per year is N. Let's take a look at a problem relating to this. So we have a savings account earns interest at an annual rate of 4% compounded quarterly. If the account begins with a principal amount of $1,000, what will its value be after 3 years? So first, let's just figure out what we're trying to find here is A. So we have A is equal to, our principal amount is $1,000. We're going to have 1 plus, our rate is 4%, but rather than writing a percent, since we're doing some algebra, what we're going to want to do is write that as a decimal, so 0.04 over, now we're compounding something quarterly. So if I'm compounding quarterly, that means that would be compounded 4 times in a year. So our N value is going to be 4, and that's to the N times T. So again, 4 times, then we have 3 years. Now, when we're solving this, we need to keep in mind our order of operations. So we want to deal with those pieces that are inside the parentheses first. So we have A is equal to 1,000. Now, 0.04 divided by 4 is 0.01. So this would be 1.01 since we're adding 1. And that's going to be raised to the 12th power. So then if I take 1.01 and raise it to the 12th power, we would get 1,000 times 1.126825, and let's see how far we're going to have to go. Now we're multiplying that by 1,000, so I just have to go over 1, 2, 3. So that A value would be equal to $1,126, and looks like that should be 83 cents. So by having your money or your $1,000 in this account, we were able to gain $126.83 after 3 years with that interest rate compounding quarterly. Okay, now the second scenario that we might have, still dealing with money and accounts, but that would be if we are compounding continuously. So in our last equation, that would be if it's compounded quarterly, like our problem, it could be weekly, yearly, biannually, which would be 2 times, so on and so forth. So this gives us a new equation, which is down here, and that's known as your APERT, where we have our amount that we're interested in is our principal amount, and then we just use E, which is an irrational number, a little bit like pi. And anytime we're using E, we're normally dealing with things that are exponential. And that would just be to the rate times time. That would be in our power. So let's look at a formula with this. So our first one, we're dealing with the same information. So we have our amount is equal to 1,000. The only thing that's different is we are having it compounded continuously. So this would be E to the 4% times 3. So that would be 0.12. So on a calculator, you would do E. Let me show you guys where that would be. If you're looking for E, that's going to be in the second option down here. So E to the 0.12 power, so we get 1.147, and we would multiply that by 1,000. So the amount we get is 1,127. And it looks like 50 cents. So we were able to gain an extra $1 just by switching the way that it's compounded. Now, obviously, if we had more money in there than 1,000, we would be able to, that would be more beneficial to us. We would get more money back on that investment. Second problem, we have after 5 years of earning continuously compounded, or after 5 years of earning continuously compounded interest at a rate of 3.5%, a savings account is worth $3,200. So this is our value. We want to know what our P value would be. So we have $3,200 would be equal to P to the E times 0.035 times 5. That would give us 0.175. So then again, I'm going to switch over, figure out what that value would be. Second, 0.175 equals 1.1912 I'll use. So I'm going to do 3,200 is equal to P times 1.1912, and we would divide both sides to get that P by itself. So divide those, and we would get our initial amount, P, is equal to 2,686 and 37 cents. Move that over just a tad so we can get that last number in there. And 37 cents. Moving right along. Okay, so here we would be using just our general formula for exponential functions. And here we're dealing with a half-life. So the element nobelium has a half-life of 58 minutes. Write an exponential equation to find the portion of a mass of nobelium that is left after X minutes to find what percentage of the amount of nobelium is left after 15 minutes. So the fact that we're dealing with a half-life is an important piece of information, because that would be a Y value with our 58 minutes being an X value. So using this, we are able to find that B value, and then we can undo things, solve for B, and then we can find out how much nobelium would be left after 15 minutes. So our equation will look something like this. 1/2 is equal to B after 58 minutes. Now, if we want to solve for B, we need to take a root with a power of 58. So that's the only way that we can cross those two things out. So I need to take a 58th root of 1/2. So I'm going to show you guys how to do that on your calculator. So the first thing I'm doing, since it's such a high power of a root, I'm going to put in that number of the root that I'm taking. So I'm taking the 58th root. Then I'm going to push the math button. If you look down here, that fifth option, we have an X with a radical symbol. So that's to take any power of a root that I could ever think of. So you can see that I'm taking a 58th root, and now I'm going to say of 0.5 equals, we got 0.988. I'll use that value. So B then is equal to 0.988. So if that's my B value, I can plug that back in, and we can say Y is equal to 0.988 to the 15th power because we're interested after 15 minutes. So let's go back to our calculator to figure out what that would be. 0.988 to the power of 15 minutes. So we'd have 83% of this element left. So after 58 minutes, half of it's gone. But after 15 minutes, we have 16.6% of it gone. So y is equal to 0.8, what was it? 834. Or if you're thinking of it as a percentage, 83.4% would be left over. Okay. Next, solving problems with growth and decay. So this is a little bit like we just did, only it's adding an extra step. So mainly we're going to be looking at values from a table. So we're going to have to work our way backwards using x and y values in order to solve for a and b. So to do that, we're going to use some things that we know about exponents. So we have an experimenter measures the maximum distance a large pendulum travels from its resting point at each swing. The measurements are recorded in the table. So our initial equation for most exponentials is this y equals ab to the x. So we have to work our way backwards in order to solve for those a's and b's because our swings are all x values, our y's are all distances in meters. So I'm going to always use that initial value. And the reason why we're going to do that is because I know that anything raised to the 0 power gives me a 1. So 1 times a is a. That means our a value is 2.17. Okay? Then we can plug that into our equation and use our next point to solve for b. So I'm going to use 1.5. Like I said, I'm going to use my next point. 1.5 is equal to 2.17 b to the third. So if I'm going to solve for b at this point, I'm going to divide by 2.17. And I get 0.6912. Then kind of like our last problem, I'm going to have to take a cubed root of both sides. That'll get b by itself. So if you want to take a cubed root, you can simply do math. And the fourth option is for a cubed root, just because that's more, that's a root that we would be more used to taking, where it's more common to do so. So we get 0.88. So since I have my a and my b value now, I simply have to plug those back into my equation and I would be able to find any value. Write this in black. So y equals 2.17 times 0.88 to the x power. So that's what we would be looking for there. So that would be the equation that's going to go along with our table. Okay, and just doing one more here. For this one, we're going to actually set up our own sort of table, or we'll kind of use the information and do it the same way. So in 1990, the U.S. Census found that the population of USA was approximately 248.7 million people. In 2000, the new census put the total population at 281.4 million people. Assuming the population of the USA shows exponential growth, predict what the population will be in 2010. So if we're doing a problem like this, I'm going to use that same type of information that I said before, and 1990 is going to be my year 0. So that means that 248.7, which is a y value, would be equal to a times b to the 0 power. So meaning that 248.7 would be my a value. Okay, plug that in. Our next year that they give us is 2000, so that's 10 years later. So we have 281.4 is equal to 248 0.7 times b to the 10th. So we're going to have to do a little bit of algebra. So we should have 1.13 is equal to b to the 10th. In order to get b by itself, we would take a 10th root. So remember, we will do 10, math, that fifth option of 1.13. So our b value is 1.01. From here, plug it back in, and then we would find the population estimation of 2010, which would be 20 years later. So we're going to have y is equal to 248.7 times 1.01 to the 20th. So we would have 248.7 times 1.22. So roughly, we would have 2010 would be an estimation of 303.46 million people. I really should put my unit in there. Hope you guys benefited from this lesson. Hopefully that calculator piece helps out. And yeah, hope you guys have a great day.